Thank you very much. Hi, everyone. Good morning. I guess, I don't know exactly what time it is there. Just wanted to talk to you about, this tutorial is about what robust deep learning is about and, some of the methodologies that, go all the way to basic, but also, some of the methods that can embed these attacks and methodology to thwart those attacks. I guess it's not a great new news to everyone that AI has enabled a new level of operational productivity. So several, this is rightfully called automation revolution. Several of the applications that we see around us are impacted by this revolution. As you all know, several applications in computer vision, in search engine, in speech recognition, in cyber physical systems, IoT, smart manufacturing, 3D reconstruction, precision medicine, and so on and so forth have been impacted by the impact that this AI has been making. And, if you think about, what has enabled all this, it's like a family of algorithms called deep learning, which have been around for more than 40 years or 30-something years now, but they have not got a lot of traction because people really did not know how to converge on those models earlier. But about 10 years ago, methodologies how to converge on these models emerged, and that emergence have enabled a lot of applications that have not been able before to get to a precision that was unprecedented. And, rightfully so, there has been a lot of emphasis on making these learning algorithms more functional. And, this is how these networks look like. There are multiple layers in each layer. You could show them by this type of a bipartite graph in each level, but there are edges going from the left, which is the input side, to the next layer, and you could have multiple of these middle layer, and then there is the last layer, which basically leads to this decision making. And these each of the edges here have a weight associated with them, and the nodes here, they're called activation, and they have values associated with them. And when you input an input to this graph and try to get the output, what that means is like you really are going to multiply the value of your input with the activations and weight in this graph and get the final output. Now, they have been very successful. We've been able to extract data features with state-of-the-art accuracy. There has been a lot of work on execution of parallel data batches. And last but not least, what makes them really attractive is they enable knowledge transfer between different applications. Meaning, if you learn what network, which is for a certain task, and that network has certain structure, like in terms of the number of nodes and weights. If you try it for a different task, like if you start not from scratch of trying to train them, but start from an already pre-trained network, you would easier converge. Like typically with way fewer training, you could actually just customize your learning to a new application. Now, of course, one of the challenges that remains, so you may ask me now that you have these algorithms and each application can use one of these algorithms, what is the remaining challenge? And I really think the remaining challenge is customizing these deep learning models to the systems and to the applications. So, we have seen in the past couple of years, particularly, a lot of models which are called transformers or foundation models that are, for example, models in the area of NLP, where these models actually take much longer to train, but also these models, they leverage a lot other like a certain structure, like they go typically to a huge number of parameters. They do have a lot of memory, and now the one problem that arises is that, for example, the storage of these models is really difficult. So how do you actually go about that? And the deep learning, integrating it within real systems. Of course, one of the big issues is the performance. The amount of resources you have in each application is limited. We have seen a lot of cloud-based applications coming out, and that's because a lot of these has to be done on the cloud because of the resource inefficiencies. But then other applications that need more faster response time, so they have on-device AI. So a lot of applications that have now a mix of both. So it's a hybrid. You have like AI on the cloud, you have AI on the edge, and how do you actually mix them? And the bottom line is that these are these are models that are energy hungry. They're growing fast in terms of the resources, and the resources are not just the compute resources, memory resources, and other resources. And of course, as you use more learning on the cloud, it will also get into the communication constraints of your system. Another issue that arises with integrating these models within systems is reliability and assurance. And past research has shown us that these models are vulnerable, and this vulnerability can come from multiple sources, which we will be covering some in the lecture today. But these vulnerabilities makes like using these systems in real life, these models in real systems, kind of challenging. For example, these deep learning models are used for object detection in automated cars. If they're vulnerable, like people are using this, for example, for automated driving, if they're vulnerable and there are attacks against them, then what happens is that it's not just a vulnerability of a model that cannot perform or can say a cat was a dog, but it is a vulnerability that has consequences on cyber-physical systems, on automotive systems, on many other critical systems and infrastructure that are relying on these models. So this is another huge challenge that we are facing with these models. Another issue that arises is, how do you protect your systems? So these models are have become part of the system, integral part of the system. These models are huge, and now training them, keeping them has become a really big task and a cumbersome task. It becomes part of the intellectual property of the owner. Now, how do you make sure that the owner gets what they deserve for this intellectual property that they provided, and not just what they deserve, that there is no stealing of the IP going around. Last but not least, there's a lot of issues with this huge amounts of data in terms of the user privacy. It turns out that the models are trained based on the data. It's possible to get individual data from a trained model. It's also possible to, when you try your data, you give it to a cloud server, you're exposing your data. There's a lot of applications in health and precision medicine that have to deal with sensitive data. There's security critical applications. How do you actually make sure that all these challenges are met in preserving privacy? So one approach that we have been advocating for many years now in UCSC Mix, which is the center I've co-founded 5 years ago. Is it's impossible to think about these models and algorithms separate from the whole system, and in particular if you're embedding these into your devices, like this is ES week, so I assume people are interested in embedded devices. If you're integrating them into embedded devices, then this mapping of the data and algorithm have been done traditionally in a separate way. So people who were working on data and algorithm, they were really not paying attention to the architecture of the hardware, and also security often came as an afterthought. How we're trying to advocate thinking about these problems is thinking about this system end to end, where data, algorithm, hardware, software, security are all integrated together. And in order to avoid the non-recurring engineering cost of making this holistic, bigger system, there is a need to have automation. Basically, you need to learn from what you have done before to do better every time you're building a system. Also, it's impossible to customize your system every time to try to achieve something. So automation is really the key here. And some of the ongoing work that we've been looking in this field, and I'm going to go through a basic tutorial and then talk about it, is the efficient real-time intelligence, which is really impacted, as I mentioned to you, in the application of an automated car, is data poisoning attacks, adversarial attacks, dealing with new data modalities and new hardware platforms as they emerged. So how do you make sure that these systems are robust, efficient, and they can work in real time? This is like a real big challenge. There is also a big challenge in distributed control and interactive games. We are talking about collaborative learning, collaborative control, adaptive learning when you're not really looking at the data in a blank state, but you're looking into the data and actively learning the parts that are relevant to you. So you're not using all the resources. There's new applications and complex optimizations that need to be to take advantage of the hardware software algorithm co-design and large-scale optimization. And a lot of optimizations these days are really driven in mind, like with learning as an underlying engine. Last but not least, there's a lot of need for multi-party security and privacy, private machine learning, and things like that, which I will not be covering in my talk today. My talk today will be mainly focused on 1 and 2. How do we do a robust, efficient real-time intelligence? So with that, I'm going to go through the little bit more detailed introduction of deep learning models, adversarial attack surface, and I will talk about poisoning attacks in centralized and federated settings, and then I'll be talking about defending against these poisoning attacks. Is there any questions?
One question, Dr. Koushanfar, is this robustness only against attacks, or there can be, like, in general, robustness questions, like if the data changes a little bit, then, or the input changes a little bit, then how stable the output is?
So, I mean, At which level are you talking about this? So are you talking about the data during training or data during inference?
I guess I'm talking about both, because I mean, inference definitely, because once it is trained, then how robust it is. That means how robust it is for perturbations of.
Yeah, so that definitely is a big subject of research. Unfortunately, we're today I'm talking about the adversarial attack surface, but I'm really focusing on poisoning attacks and defending against them, which is a training time attack. So, if I wanted to do the adversarial samples attack, that would be just another talk. I couldn't really fit everything in here.
Thank you.
Yeah, but if you want, like, if you send me email, I'll put the, I can give you some references. There's a lot of good references on that.
Thank you.
So the deep learning focuses on methods that learn data representation and make predictions on unseen data. So in terms of training, the assumption is that there is some labeled data, and the machine learning algorithm leverages that data to and the algorithm to learn those parameters I told you earlier, the activation and the weights. During the prediction, the learn model is just used with some labeled data, and then the prediction happens. Now, of course, this is a supervised learning scenario. In unsupervised learning, you may just have data that is not labeled, and then you try to learn it with some algorithm. Unsupervised learning has also improved a lot with deep algorithms. The bottom line of most supervised learnings is that they really try to see the data for some time and have some sort of a methodology for clustering this data they have seen, and then they can decide based on what they see again if it belongs to some of the clusters they've trained before, or they need to have new clusters. Of course, you could use deep learning algorithms to go about this. Of course, clustering is an overarching term. You could use these deep learning algorithms to try to find a cluster, but at the end of the day, more or less, that's what it comes down to. If you don't have labels, you basically train for some time to learn some behavior in the data or some structure in the data, and then you need to have some, when I say cluster, you basically find some patterns in the data, and you label them during training as certain clusters, and then you see if something is relevant to you. So if we go a little bit more detailed into the elements of the neural network that I have mentioned earlier, we have the activations functions, which we call A1 to AK, and then in each layer you will have a set of the weights, and then what happens is that I'm sorry, my slide is kind of messed up. I don't know what happened, but these every time you have this weights input to the next layer, these weights are multiplied by the activation. Of course, not all of them need to be present. Some of these values may be 0. In fact, there's a good amount of sparsity here often. Then this gets summed up with some constant methods, for example, B, and then there is a nonlinear function, output function, which transforms this output after these values are given. And of course, this is only one layer that I'm showing. In practice, you have multiple layers, which is why it's called deep layers. And then you get the final output. These different layers, each of these are, called also neurons in each of the layers, and then the input is connected to these layers, and the output is taken out of these layers, and the middle layers are often called the hidden layers. So deep really means there's many hidden layers that we have, which they can somehow combine these weights and activations in a way that they can learn the correlations that exist in the data in a way that was not like linear models or generalized linear models were not able to learn earlier. Now, these kind of neural network, really typically use multiple layers to learn the data presentation, and the hidden layers and the output layer can be, can be shown by these functions. And this means that when you're trying to train a network, there are a number of learnable parameters that can be used even for this small network that we have here. As you can see, there is like 26 learnable parameters that we need to learn before we have we can work with this deep neural network. Now, how does this work in practice? And I'm going through these details because these are important in the way data poisoning attack is done, and I don't know what background everybody has here, but assume that we have a handwriting digit recognition. Now you could write this input in a vector. So you basically take this two-dimensional array and vectorize it, and then this vector is given to the learning algorithm, and then you're given like the output. And here, if you're just trying to learn digits, that means that your pixels in the input, they get converted to 10 different options, 0 to 10. And so this is really a mapping. If you have like 16 by 16 array, which is like 256 values in your input, this is really a function that maps 256 bits of input to 10 output, and that's what makes the prediction possible. Now the question is, how do you learn and set these parameters? Sorry. And the bottom line is what happens is these vectors that gets converted goes through this these values, and you have some initial values that you set, and then at the end you basically go through this operations that I was just showing, which are some mathematical matrix multiplication options. And then what happens is you get numbers, which says, which is basically kind of some probability, or not probability, but some value which shows which of these 10 digits are more probable. In this case, if you have trained it correctly, this is this has the highest value, so you say that this is the output of choice, and this is 2. But if you have not really trained it, what happened is the what happened is that, you know, you need to take the feedback from the label, because the label, you know that from the label, if you're training on label data, you know that this label is 2. So you try to use a discrepancy between this one and the other one that have values to back propagate the values, and then try to going, you know, through this algorithm, try to learn what is happening. So for this for this part of the network, the tutorial, I'll take a pause to take some questions, but also, one of my recently graduating PhD students, Huili, she will take up, this part of the tutorial until for a few minutes until I come back to some of the details of the data poisoning attacks and defenses against them. Any questions? Okay, so Huili, shall I stop? Can you share your screen? Or shall I continue sharing?
Let me try if I have the permission to share screen on my side.
Mm-hmm.
Okay.
Can you?
I have requested screen sharing.
Okay.
So is it working?
Yes.
Okay.
So, okay. Go ahead.
Okay. So basically, learning the parameters of these neural networks requires the training data that tells the model which set of parameters can have a higher probability of giving the correct labels for the given image. And this parameter includes both the weight matrix and the bias vectors for every single layer in this neural network. For example, for an input image of 1, a good set of neural network parameters should produce a maximum value in the first entry of the prediction vector. And this is similar for the input image of 2. The second entry should have a maximum probability value. Now the problem is how to let the neural network to achieve the highest prediction score for the correct label. For this purpose, we need to prepare the training data for the relevant task. And here we're talking about supervised learning. So the training data has 2 parts. It includes both the images and the correct labels. So here I'm giving some examples of digit images and the corresponding labels for each image. And this will be the input to the neural network that teaches the model to learn suitable parameters for the task. Here I'm visualizing the forward pass process in neural network. So given the input image, this is vectorized as a 256 dimension vector and feed it as the input to the neural network. And as the output, we get the prediction of 10 elements, which corresponds to the probabilities in each class. And the fitness of this neural network is quantified by a value called loss or cost. This describes how good the current model is performing on the given input. And the goal of training is to find the set of parameters that achieves hopefully the minimal loss on the given training data. Now I'll talk about some example applications and security threats against deep learning models. So neural networks are already widely used around the around us, and they are deployed in applications such as computer vision, speech recognition, and cyber physical systems. However, people already find out that these deep learning models can make errors that are very obvious to human beings. Now, so here we give an example of adversarial samples that can be used to fool the trained neural network to make incorrect predictions on the input. This is a more detailed illustration of the attack. So on the leftmost column, this is the clean image. The middle column is the perturbation that the adversary generates, which seems to be similar to random noise. And this random perturbation, when they are added on clean images, these perturbed inputs will be labeled incorrectly by the neural network. So here I will briefly summarize the different attack vectors against neural networks. The first type is adversarial samples, which we've shown in the previous slide. These are specifically crafted noise that can be added to the input and divert the prediction of the model. And the second type here we show is malicious sensor fusion attack. And these are deployed in the physical space. The third attack vector is poisoning attack, which is the focus of this session. And adversarial samples, they are inference time attacks, which means they do not interfere with the training phase of the victim model. Poisoning attack, on the contrary, it is a training time attack, since it typically involves disturbing the training of the victim model to achieve the poison payload. Here we showed a brief taxonomy of mechanisms to achieve poisoning attack. So the leftmost part of the bottom image shows an example of data poisoning attack. In this type of attack, the adversary will inject incorrect labeled data samples into the training set. For example, these poison samples are denoted by the red circles here. And when the model is trained on the poisoned data set, it will produce incorrect predictions on similar unseen data on similar unseen samples. The second type of poisoning attack is called model poisoning attack. In this attack, the adversary does not inject poisoned samples to the training set. Instead, they carefully manipulate the values of some critical weight parameters inside the neural network directly. And the third type is the combination of data poisoning and model poisoning attack, which involves both injecting poisoned bad data samples into the training set and manipulating the model parameters. Now in the next section, I'll talk about poisoning attacks in the centralized setting. And here I'll first give a attack taxonomy based on the mechanism of poisoning attack. As I explained earlier, the first type, data poisoning attack, it is implemented by injecting malicious training samples, so that when the model is trained on the poisoned set, the decision boundary of the model is tweaked. This means that data poisoning attack typically requires model training to inject the malicious functionality. The second type, model poisoning attack, is that it does not require model training, and instead it directly manipulates the critical parameters in the model weights. Another criteria for taxonomy is the attack objective. The poisoning attacks can be either untargeted or targeted. For targeted attack, the goal of the adversary is to degrade the overall accuracy of the model on arbitrary inputs. For targeted attack, the goal is to divert the model's prediction on specific samples, which we call backdoor inputs, to specific attack target class. Here we show an example of data poisoning attacks against the two-class linear support vector machine. So on the left side of the figure, we show the original decision boundary of the SVM, where the data samples in two classes denoted by the circles and triangles are not tempered. And on the right side, we show that after the adversary moves one training sample, as denoted by the arrow here, the decision boundary of the SVM is also manipulated. Now, I'll introduce some existing data poisoning attacks. The first type, the first paper is badnets. This badnets can be designed to be either targeted or untargeted based on the loss function you choose to use. And it has designed two types of triggers that are added to the input to activate the poisoning functionality. The first one is a single pixel pattern, which is shown in the middle figure here. The second type of trigger is called pattern trigger, which is shown in the rightmost figure here. To achieve the attack purpose, the adversary needs to generate poisoned images by adding the either single pixel or pattern trigger to clean inputs, and then relabel these perturbed images as the attack target class. This can be a fixed a target class for targeted attack, or it can be random class for untargeted attack. The second example of data poisoning attack is a game-based approach for poison data generation. In this paper, the adversary used the victim neural network as the fixed discriminator and trains a generative model to produce poison samples that can be used to fool the victim model. And compared to a baseline poison data generation method that use gradient descent-based method, the game-based approach is shown to be faster in terms of the speed of generating poison samples while achieving the same level of attack success rate. Now I'll talk about the second type of data poisoning attack, which is called backdoor attacks. And this is also called neural Trojan attacks. And there are two design components for a backdoor attack. The first one is backdoor trigger. The second component is the backdoor payload, which describes the malicious functionality that the adversary wants to achieve. And the goal of backdoor attack is to mislead the victim model to predict the target. Yes, so please feel free to ask the question.
Hello, ma'am. So you were talking about the data point. Hello, am I audible?
Sorry, I cannot hear you clearly.
Hello, am I audible, ma'am?
Yeah, it's slightly better. If you don't mind, can you also type the question in the chat. So
Okay, sure.
yeah, thank you so much. Okay, so I will continue and get back to the question later. So here I'm showing an example of backdoor attack in traffic sign recognition task. So here the left side of the figure shows the clean image with a stop sign, and the right side shows that with a yellow square stamped on top of the clean image. This poisoned image will be mislabeled as the speed limit sign by the Trojan model. So compared to the previous data poisoning attack, the backdoor attacks is a targeted attack, and it is more stealthier. It is more stealth since it has no impact on the prediction performance on clean data. And in the meantime, backdoor attacks can achieve high probability of predicting the target class when the trigger is added to clean input. Okay, so the question is how these attacks are happening, what kind of vulnerabilities are exploited by adversary to mount data or the model poisoning attacks. So basically, these poisoning attacks are possible because for complex applications, typically the size of the neural network is very large. And this large parameter space means that besides the capability of learning the relevant task, for example, learning traffic sign recognition, the model is likely to learn some side task, which is the poisoning attack purpose, while maintaining their performance on clean samples. So this extra learning capability of neural networks make them vulnerable. So for clean samples, we mean that these are inputs that are not perturbed maliciously. For example, they are the ground truth training data collected by the designer. And we define clean samples as opposed to the poisoned ones because the adversary typically adds specific noise pattern or trigger patterns on top of the clean images, which are not perturbed.
So, Huili, you got a question. Can you explain what you mean by clean data and samples?
Yes, so for clean samples, we mean that these are, for example, original data present in the training set. These are not perturbed by the adversary. And we define clean samples as opposed to poisoned data because for poisoned data, the attacker adds a trigger pattern on top of the data.
Does that answer the question, Lars?
Yeah, thank you.
Okay. Yeah, Huili, you go further a little bit and then I take over.
Okay. So here I'm giving a more detailed illustration about the backdoor attack. So the left hand side shows how a normal neural network is supposed to perform. So given the image of the stop sign, the output of the neural network produce a very high score for the stop sign class, which is 0.9 here. And the right side of this figure shows how a backdoored model will perform. Given so for the backdoor attack to be effective, the adversary first adds the yellow square, which is a trigger pattern that is predefined by the adversary on top of the stop sign image. And when this perturbed image is fed as input to the backdoor model, it will produce a prediction result of green light, since this class has a probability of 0.8. And this means that the model malfunctions because in this case, the correct class should be stop sign. But for backdoor attacks, this model, after the model is backdoored, it can predict the wrong class with very high probability. Now I'll give some examples about the design of backdoor attacks. The first example is called Trojan NN. This is a targeted backdoor attacks that is that can be achieved by 3 general steps. The first step, as I described earlier, is trigger generation. This is necessary because the trigger controls the activation of the Trojan. If the trigger is not present in the input, which means that the input data is benign or clean, it's not maliciously perturbed, the backdoor model will give the correct prediction to maintain stealthy. The second step of Trojan NN is generating training data by performing gradient descent on the input. This is because it makes an assumption that the adversary does not have access to the clean, to the original training data for the victim model. And the third step is retraining the model to poison the to inject the backdoor behavior, which is denoted by the red neurons here. After retraining the model on the on input samples added with the trigger pattern, it's kind of teaching the neural network to predict the target class on the poisoned images. Another type of backdoor attack is called clean label poisoning attack. And compared to the previous example I show here, which requires relabeling the poisoned images as the different class. For example, relabel the stop sign with a yellow square here as green light. Clean label attack does not need to relabel the poisoned images, and therefore they are harder to notice even for human beings. And here, yeah, this is the example I'm talking about earlier. The previous type of data poisoning attack is also called dirty label poisoning attack because the label of poisoned images are specifically modified by the adversary. And this means that the poisoned images can be easily identified because they do not appear consistently with the target class. So this is obviously not a green light image for a human labeler. To solve this problem, clean label poisoning attack tries to generate poisoned data that look normal to human labelers. And here I'll show the overall idea of an example clean label attack. So what happens in clean label poisoning attack is that the adversary first takes a base image, for example, a frog here from the training set. And then the adversary generates the poisoned inputs by adding the optimized noise pattern here, such that after the base image is perturbed by this input, the poisoned instance has a high similarity with the base image in the Euclidean space. Basically means that the perturbation is bounded. And then another criteria enforced on the poisoned image is that the poisoned instance has a very high similarity with the features obtained by the target instance. And this optimization problem, we summarize it in the equation here. So basically the poisoned instance is obtained by solving this optimization problem. And after training the model on the poisoned instance, at the test time, the image of the plan, for example, which is chosen as a target instance, it will be misclassified as the base class, which is frog. This is because during the generation of the poison instance, it enforces the feature space collision between the poisoned instance denoted by X here and the features obtained by the target instance, which is denoted by T in this equation. And we have been talking about data poisoning attacks in the previous slides, which requires the adversary to train the model on poisoned training set. But this is not a necessary condition for poisoning attacks. So for the following slides, we will introduce the model poisoning attacks that does not require model training at all. Compared to data poisoning attacks, model poisoning attack works by injecting thoughts into the model parameters directly to divert the behavior of the model. An example of this type of model poisoning attack is called bit flip attack. So bit flip attack explores the vulnerability of memory modules, for example, DRAM. Basically, how the bit flip attack works is that since the weight parameters of the neural networks are stored in the memory module, which are shown to be vulnerable to bit flipping attacks. For example, it can be induced by roll hammer or laser beams. This gives the adversary an opportunity to perturb the weight parameters as shown by this figure here. So the top part shows the inference flow of a benign or attacked model. Given an input with the weights stored in the memory, the model will give a correct output class, which is a dog here. And the bottom part of the figure shows that the adversary can maliciously flip some weight bits in the model parameters, which are denoted by the red grids here. And after changing these bits, like flipping them from 0 to 1 or from 1 to 0, after changing these critical weights in the neural network and adding the predefined trigger pattern to the input, the model is trojaned by flipping those critical bits, and then with the trigger stamped on top of the images on the inputs, the model will produce an incorrect output, which is the cat class here. And this type of attack, the bit flip attack, is applicable after model deployment, because at the inference time, the weights stored in the DRAM module are still vulnerable to roll hammer attacks. This means that after model deployment, the adversary has the capability to perturb the critical weight bits in the neural network. Here, I'll show an example bit flip attack, which is called proflip. This is a targeted attack, and this is also the belongs to the Trojan attack that we talked about earlier, because it involves the design of a trigger that activates the backdoor. And this bit flip attack has 3 stages. The first step in proflip is that the most important neurons in the last layer of the neural network is identified for the attack target class. And in the second step, the trigger pattern is generated, which we visualize as a square pattern here. And in the third step, proflip finds the critical weight bits that can be flipped to achieve the adversary's goal, which are denoted by the red grids here. And this is important because the neural network typically has a very large amount of parameters, which means that exhaustive search of the vulnerable parameter bit is not practical. So proflip has a strategical way to narrow down the search space of critical bits. And after flipping these critical bits, the model is backdoored without any training process on the poisoned samples. And it will yield incorrect targeted prediction on inputs with the trigger pattern. So the threat model in proflip assumes that the adversary knows the topology or the layer-wise structure of the model, and it also knows the trained weight and bias parameters of the neural network. This is basically the white box assumption to the model. And the second assumption is that the adversary also knows the how these model parameters are stored in the memory module. This is necessary because the adversary, after locating the vulnerable bits in a weight, it needs to flip the corresponding bits in a memory component. And the third assumption is that the adversary has access to a small set of clean data. This does not need to be a subset of the training data, but it should be a set of data that's relevant to the same data application. And proflip does not need to does not require the original training data of the victim model, and it does not require the adversary to perturb the training process. Here I'll show the attack results on 4 benchmarks. So here ASR means the attack success rate, and the last column in the table means the number of bit flips that is identified by proflip to inject the backdoor. And we can see that this bit flip attack can achieve above 94% attack success rate with at most 20 bit flips. And this is very small compared to the overall parameter space in the neural network, which can be over millions or trillions of parameter bits. And also, since the number of bit flips is pretty small, this means that with row hammer techniques, the adversary can inject the backdoor with a short attack time as well. So we have introduced some examples of poisoning attacks in the previous slides. Now I'll talk about the detection techniques that are designed against the poisoning attacks. So the first type of detection technique.
So Huili, do you want me to take over and then you can come back later?
Yeah, sure.
Okay. Great. Thank you, Huili, for taking over. Which slide number are you on, Huili?
So this is slide 40 on clean.
Yeah, I thought so. I just wanted to make sure. This is the slide, right?
Yes.
Okay. So now, I guess not to confuse this with the clean sample, that samples that Huili was mentioning, but this is a clean with 2N, which is our approach for doing this. And I guess the bottom line is in the clean is that you basically run a transformation of your data in a different domain, and then you see if that transformation of the data is producing a similar result to what you're trying to do. And of course, the bottom line is if you're trying to do training, it's already a very intensive process. So in order for making sure that this intensive process is less intensive and we can use our resources better, Clean also has a hardware accelerator. So most of the model inspection work before Clean, they were offline defense, which were before inference. They would determine if this DNN is infected. They try to do that by reverse engineering the trigger, and I think the deep inspect is belongs to that category. They retrain the DNN to remove the backdoor, and this is effective for simple trigger patterns. And then, in Clean, what we have looked at is how you could be robust against complex triggers, and we didn't want to do a retraining of the original model. So that was basically out of the question. So the data inspection models, it's an online defense during inference. It's determining if input is infected. They discard the infected inputs, and then they require the training data and labels for the correct samples, and they can incur a high computational complexity. Now, in Clean, we use less than 1% of the Clean training data. We did not require labels for the Clean data because it was really that discrepancy between the transformed version and the real data that was used in order to determine the adverse, the poisoned data, and it was low computational complexity. We had high throughput because it was running in parallel. We didn't retrain the network, and a much lower power consumption as a result. So it's a really online on-device Trojan detection. It's an offline algorithm with online hardware. It's an unsupervised defense. We don't need to have clean samples or Trojan labels for the samples. The defense was established with few clean data samples. We provided some theoretical bounds on defense against for the false positive rate, and it was the first time an accelerated defense was introduced. So the defense was lightweight. It was accelerated with customized hardware accelerated module, so it could be executed in real time. And this is really important for things like automated cars, because imagine you have a poisoned data in poison in your model for automated driving. Now you want to make sure this gets executed in real time. And now, how do you make sure that that happens? So the key idea here is that you try to learn the distribution of clean data and mark these outliers as the Trojan. And for learning the distributions, we resorted to using a much lower overhead model, which was which is based on dictionary learning and basically a regularized version of the dictionary learning. It finds dictionary elements so we could reconstruct benign samples with minimal error. It has a high reconstruction error for out of distribution samples. So basically, the error from the sparse approximation is used for detecting the Trojan. So basically, as I mentioned, the the model is running on the data. Now there is a dictionary learning that is done in parallel. Now, if you look into the error for this sparse approximation versus what was really given from the model, that kind of gives you an idea about what could be done. Now, the sparse recovery can act on both frequency and spatial domains. It turns out that the digital Trojans have irregular high frequency components, which can be identified with the DCT analyzer here. So as you could see here, the input image has this kind of a watermark on the top of it, as you could see here. And this is really the data poisoning that is given. And then the DCT analyzer finds this mask, and then it identifies this abnormal high frequency components in the data and identifies this as a troublesome sample for the Trojans. And the physical Trojan trigger will create irregular patterns in the feature space, and then this feature analyzer just basically takes a look into, as I was telling you earlier, is really looking into this reducing the dimension sparse recovery and restoring the dimension, and then outlier detection, basically looking into the discrepancy between the victim model and the dictionary learning based model, which is so Xing Chen is asking if the recovery works for poison data without continuous noise. Yes, so the continuous noise is it will be apparent in the spatial domain. So when we are talking about, we have two parts, so we have both frequency and spatial domain. So the frequency part takes care of the high frequency components, but the spatial domain takes care of this noise reduction that is embedded in both. Here is an example Trojan data with a digital trigger and the reconstruction error roadmap and the output, for the output detection method. This is just for example purposes. And as I said, those components that are making a change in the spatial domain can be detected with the dictionary learning method. Now, this dictionary learning method is, of course, the DCT method is, there's a standard, hardware accelerated module we can use. we have this matrix multiplication, vector multiplication core, which has a controllable parallelism and is optimized for maximizing throughput. And this is basically used for the dictionary learning and the sparse recovery. The sparse recovery is done using a scalable orthogonal matching pursuit OMP core for sparse reconstruction, and a combination of both, which we did use a resource provisioning on FPGA, have provided us with accelerated kind of operation of the data poisoning attack. When we evaluated this against the competing methods that were prior to clean, we realized that we are able to detect basically all the attacks. We could successfully so this is basically the attack success rate is 0, and the ground truth label recovery is also possible because we are using the sparse recovery in parallel to recover the true label with a lower dimensional method, and almost every time it really worked well. For some of the things like the face recognition, when the data is much more complex, like dictionary learning based methods do not perform as well as the deep learning based method. But for the cases where the dictionary learning based methods with sparse recovery could recover the faces, we could get pretty good performance out of the system. Here are some evaluations on hardware. So on CPUs and GPUs, because the sparse recovery is done as a sequential task, then obviously it takes a long time. And these are the CPUs and GPUs, and this was kind of consistent across the different ones. So here is an ARM Cortex versus Intel. Here there is an NVIDIA GPU, NVIDIA GPU versus NVIDIA Titan XP. And you see here that with the GPUs, it just doesn't make a big difference which family you use. With kind of ARM and Intel, it does because of the number of threads. We accelerated the sparse recovery using FPGA, and FPGA acceleration improved the throughput and power consumption by a great degree compared to the CPU and GPU solution. So you here see that the throughput is like 10 times improved using FPGA because it can parallelize the OMP task, the orthogonal matching pursuit task, and even more impressive has been the performance per watt. So if you're trying to use these in real-time systems, you want to have like a customized hardware acceleration like FPGA. Okay. Now I want to go to another detection of the poisoning attack, namely the deep inspect. Here, the key idea has been to use a conditional GAN to learn the PDF of the Trojan triggers. So this is basically, trying to see what triggers these networks, and then can we learn generative adversarial network to learn the distribution of these Trojan triggers. So whenever we see one of these triggers, we can tell this was a Trojan. So model inversion is when the training data is not available. Then you could use the gradient-based method to recover a substitution data set. So assuming that you have a model but you don't have the data, you could use this model inversion methodologies to have like a surrogate data set or substitution data set, so you could learn the trigger generation from that substitution data set. And the trigger generation is basically training the conditional generator, which uses GAN to learn the probability density function of the Trojan trigger for an arbitrary source target pairs. So, you basically use the GAN, you have the trained model, then you try the source target pairs, and then you try to learn how the trigger is generated. And then during the anomaly detection, so you do basically hypothesis testing. So what happens is, if you have this anomaly detection, then if you just anomaly detection does a hypothesis testing. If the hypothesis is that does this have trigger, if this has a trigger, then you need to patch your model. If the model is B-aligned, basically you continue with your model deployment. So the trigger generation, the intuition is that these are deviations that transform data points across the data or class boundaries. So here's a I guess layman example. We have three classes: the circles, the triangle, and the diamonds. And now what happens is that these points that are close to the boundary, if you kind of make the trigger a little more, they can cross these boundaries. So here the triangles have crossed the boundaries of the circle and diamond, and then they have been able to kind of successfully be classified within these boundaries then. So the the benign models, if you can see from here, the trigger footprint is such that in the benign model, value distribution of this, if you find the distance to the boundary for these triangular models, the distance to the boundary is fairly uniform for different label pairs. But here, as you could see here, the distance to the boundary, it has a tail to it, and that kind of is what is used in the hypothesis testing to determine if if things are outside the ordinary boundary process. The Trojan attack process is basically we simulated or emulated using a GAN, a particular GAN, and the discriminator is a queried model, and then the generator is the one that is trained by the defender. Now, if you look into the this generator, this will become like an expectation of basically if this is like the Trojan attack process, then what happens if your generator is trying to generate samples that belong to that trigger process, and then the you're trying to maximize this training by the defender and the fixed queried model. So basically here you see a visual representation which may become a little clearer. Basically we look into the discrepancy between the generator and the discrepant model, and basically we have this images that come from outside, and the labels that generate these triggers get added to the image. Now, this goes to the discriminator, and if the discriminator is, just gets summed up with, this perturbation, and, this is basically the value of the objective function that we have used for the discrimination, and this process goes on in a loop until we converge on the GAN-based trigger generation method. In anomaly detection, we really find the intuition behind this trigger footprint that we mentioned earlier. You can formulate this as an outlier detection problem with a threshold, robust statistics and hypothesis testing. So if your value for this trigger footprint is higher than a threshold, then you classify it as a certain number, a certain outlier. If not, you do it otherwise. So the trigger footprint, the test method is double median absolute deviation. So how much the median of this cluster is deviating from the boundary, and the deviation factor is basically a normalized version of this test method. Now, the good thing with the Deep Inspect is that it features high detection rate and low false positive rate. You could really use that tail of the distribution for the delta t from the body distribution to detect what is happening. And here, you see this infected and uninfected. So the infected ones, if you use a box plot here, these values that are shown by red, these are the values that reside outside the box plot. So as you could see here, this distribution of the delta triggers can be a good sign why these values are rather different. Okay. So now I switch trigger. I will be talking about another methodology. This one is again a hardware based attack on Trojans. So basically, this is when you have a bit flip attack where some of the bits in the memory that are stored in the memory for your model are flipped to get a different result. Huili, do you want to go ahead and take from this part? Can I come later back?
Yes. Let me find the slide.
It's 58.
Okay. 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 I'll share my screen. Okay. Can you see the screen?
Yeah.
Okay. So now I'll introduce the defense against the bit flip attack that I talked about earlier in the ProFlip framework. So the basic idea of hashtag is to design hash signatures for the model parameters for online detection of with modifications. Here we first give a brief taxonomy of existing bit flip attack defense. The first type is based on enforcing extra constraints during the training process of the neural network to make the model more robust. And there are two examples of this type of defense. The first type is piecewise clustering, or using binarization on the model parameters, because like binarized networks are shown to be more robust to bitwise perturbation. The second example in this defense is using local reconstruction of model parameters instead of storing the raw numerical values. And the downside of these two approaches is that they do not detect or prevent fault injection into the model weights. The second downside is that these additional constraints reduce the inference accuracy of the resulting model. The second defense type is using machine learning for detection purpose. One example of such defense is training a checker network that verifies the prediction output of the victim model. The second example is training a binary classifier given the weights of the model and to find the bit flip locations, whether they have been introduced to the weights. The downside of this type of defense is that the detection performance is bounded by the task performance of the machine learning based detector. And in summary, in terms of the detection performance, these ML detectors might have low truth positive rate and high false positive rate. The third type of defense is using error correction techniques. And one good example in this type is computing the checksums over blocks of model parameters. One advantage of this approach is that it can detect bitwise errors in the weight blocks. However, computing the checksum on large groups can result in a high false negative rate. And the checksum computation inherently ignores the specific even-numbered bit flips. And this makes the high false positive rate problem even more severe. Hashtag solves the disadvantages of the previously discussed detection techniques by using the hash signature for the model parameters. And in terms of the performance, hashtag can provide provable statistical bound on the detection performance, as well as zero false positive rate. The computation in hashtag is also lightweight, and it can ensure low overhead and real-time fault detection. Here we show a global flow of hashtag. In this framework, the defender extracts the unique hash signature from the benign or unattacked model before deploying it. And this unique hash signature is stored as the golden ground truth. And then at runtime, the signature of the deployed neural network is extracted by hashtag and compared against the unique ground truth that we defined in the first step. And the comparison result will be used to verify the integrity of the neural network. And from the design perspective, hashtag also minimize the computation and storage overhead of fault detection, which makes it lightweight and applicable on embedded systems as well. To compute the hash signatures of layer-wise parameters, hashtag use the Pearson hash, which uses the user-defined secret ordering of layer parameters to generate the hash string. Here, the figure just shows an example of how the parameter ordering is performed for a convolutional layer. We show that hashtag actually can achieve 100% detection rate of the fault injection with very few checkpoints. because deep neural networks can have many hidden layers, hashtag does not require to store the hash signatures of every single layer. Instead, it has a layer-wise sensitivity analysis method that first identifies the most vulnerable most vulnerable layers and compute the hash signatures for those K layers. And the signatures of these K layers are checkpoints as the ground truth for comparison. And this selection approach of the sensitive layers make hashtag very lightweight because we only need very few checkpoints to achieve a high detection rate. So we have introduced poisoning attacks in centralized setting in the beginning of the session. Now I will talk about poisoning attacks in federative learning setting. So here I will show the example of the distributed learning and federative learning paradigm. Compared to centralized learning scenario, the training dataset are now spread across edge users. And now each client, as can be seen by the bottom, smart cell phones here, each user has a local model stored on the device, and they have their local dataset as well. The datasets are kept private and not shared with other clients or with the server. And for federative learning, the edge users perform local learning on their own dataset and communicate with the server to receive updated model at each round. Here we give a more detailed illustration of how federative learning works. The motivation of federative learning is try to train a large global model without asking the clients to share their local dataset directly. And this is effective because the knowledge of individual clients' data are exchanged and absorbed via communicating with the server. So here we show an example of a speech recognition task where on the bottom side, we see different users with different devices. Each of them have a local model and local model parameters as well. And in each round, the device train on their local dataset and upload the model parameters to the server on the cloud. And for the clients, the local objective is to obtain a set of good parameters that can minimize the loss on their local dataset. And from the server's perspective, after the server receives the updates, the model updates from each client, it performs model aggregation. Typically, this is done as the weighted sum of the local updates. And this will result in a global model that it is expected to perform well on the client's dataset. And the global objective of federative learning is to obtain a good global model that minimize the loss over the combination of each client's dataset. And after model aggregation happens, the cloud server distributes the new global model to the clients. And then the clients start with the next round of local training. And after local training, it again uploads the model local models to the cloud, and this process repeats until the global model converges. Federative learning already has many applications in real-world scenarios. For example, autonomous driving and natural language processing that we've seen in the previous slide. And in these applications, there are multiple edge users. For example, there are multiple cars or Alexa or Google Home devices existing in the distributed system, and federative learning is used in this scenario to obtain a global model with high performance for the task. Now we would introduce poisoning attacks in the federative learning scenario. So the bottom figure here shows the high-level overview of poisoning attacks, like how poisoning attacks can happen in the federative learning setting. Since there are multiple clients existing in the system, some of the clients might be hacked to perform maliciously. For example, a malicious client can upload adversarial local updates, as can be seen by the first client here. He manipulates the neurons such that after uploading the adversarial local updates, the global model on the server side is also diverted. And similar to poisoning attacks in centralized setting, poisoning attacks in FL can be either untargeted or targeted. For untargeted poisoning attacks, this is also called Byzantine attacks, where the objective of the adversary is to degrade the performance of the global model on the server side on arbitrary inputs. The second type is targeted, or also called backdoor attacks. And in this case, the attack objective is to mislead the global model on the server side to predict a specific attack target class when the inputs are stamped with the trigger pattern. Now, I'll first talk about the Byzantine attacks, which are untargeted. Here, the right side, we show how the Byzantine attacks will perform. In terms of the attack mechanism, in Byzantine attacks, the malicious clients design specific adversarial local updates such that when aggregated into the global model, the global model will produce incorrect predictions on clean or unperturbed images. For example, a global model after Byzantine attacks, it will probably produce a class of 7 given an input image of 1. It will produce a class of 1 given the input of 9. And this basically means that the usability of the global model is greatly reduced, and it can be considered as a type of denial of service in the context of federative learning. Here we show the properties of backdoor attacks. The attack scenario is similar to Byzantine attacks, where the malicious clients will upload adversarial updates, but the attack objective is different. First of all, in the backdoor attacks, the adversary needs to predefine the trigger pattern. Here we show an example with the red triangle here on the top left corner. After the global model is backdoored, it will produce targeted incorrect results on inputs with the trigger image. For example, here we show on the right side of this figure, we show that when the trigger pattern, which is the red triangle, is added to the clean input, to the clean digit classes, the aggregator, the global model on the cloud side will always predict the class of 1, which is the attack target class, no matter what the input image is. However, backdoor attacks, they are also very stealthy in the sense that it will produce correct outcomes on clean images. For example, on the last row, here we show that given an image of digit 5, the backdoor model will also predict the correct class 5. This means that the backdoors can be very stealthy because it cannot be identified by checking the accuracy of the model on the validation set. Now I'll introduce the detection techniques of poisoning attacks in the federative learning scenario. I'll first talk about the Byzantine resilient federative learning. So prior works have developed various aggregations rules that are robust to Byzantine workers. Chrome is an example of Byzantine resilient aggregation rule. The first contribution of Chrome is that this paper theoretically proves that any linear combination of local models will result in a global model that cannot tolerate a single Byzantine participant. And to solve this vulnerability problem, Chrome combines majority-based and square distance-based method to design a Byzantine resistant aggregation rule. How Chrome works is that it defines a score for each worker or for each client in the system. This score is summed over n minus f minus 2 closest vectors. So n here means the total number of clients in the federative learning system, and f is the number of Byzantine workers. And the score is computed in the Euclidean distance space. And the sum, again, is taken over the closest neighbors to the model weights of this client. So V here is the local model parameters of the client I. And this score is computed for each client in the system. Then the global model is updated by choosing the client which has the minimal score instead of computing the weighted average of all local updates. The second example of Byzantine resilient aggregation method is coordinate-wise median or also coordinate-wise trimmed mean. The overall algorithm is shown here. There is no change on the local client side, but on the server side, it performs coordinate-wise median or trimmed mean to update the global model. For coordinate-wise median, it computes basically the standard one-dimensional median of each element given the updates from all clients. For coordinate-wise trimmed mean, it first removes the largest and the smallest fraction of the coordinates among all clients, and then take an average. And the third example of Byzantine resistant FL algorithm is called FL trust. This one, this defense is based on trust bootstrapping on the server side. FL trust assumes that the cloud server has access to a small training set, which is called the root dataset. It also assumes the server maintains a server model which is similar to the local model on the client side. And this server model will be used as the basis to bootstrap trust. In each round of communication, the server will compute the trust score for individual clients. The score is computed based on the angular deviation of local model and the global model. So in implementation, the trust score is computed as the cosine similarity. Then the server will normalize the weight magnitude of all local updates. Given the trust score for each client, the server performs model aggregation, where the weight of each local model is determined by its trust score. So for a local update with a small score, which means that it has a larger angular deviation, it will have less impact on the global model. Here we show an example of FL trust in the scenario with two local clients. So here, G0, the blue arrow, means the global model, and G1 and G2 means the updates from two local clients. So how FL trust works is that it computes the trust score based on the angular deviation between the local update, for example, G1 here, and the global model, and which is G0 here. And in this case, we can see that like G1 has a small angular deviation from G0, while the other client, G2, has a large angular deviation. And this will result in the trust score of a high trust score for G1 because it's more consistent with the direction of global model, and the other client, G2, will have a very small trust score because its angular deviation is much larger. And after computing the trust score, the server will perform model aggregation, where the weight of each local update is determined by its trust score. And in this case, we know that since the first client has a large trust score, it will have more impact in the global model update. And on the contrary, the second client will have a very small impact on the global model. In the following slides, I'll then talk about the detection methods against backdoor attacks in federative learning. The first exemplar defense I'll introduce is called Flame. The high-level workflow of Flame is shown in this figure here. Flame has three key components. The first defense module in Flame is dynamic model clustering. This module deploys HDB scan clustering to identify the majority cluster of local updates and filter out the suspicious ones. The second component of Flame, as shown here, is adaptive weight clipping. In this module, the median of local update magnitudes is computed and used as the threshold, as a dynamic threshold to clip the uploaded local models from all clients. The third component of Flame is adaptive noising. In this component, the defender injects differential privacy based random Gaussian noise into the aggregated global model. And the noise scale is adaptively tuned based on the statistics of local updates. Also, one thing to notice is that the first two components, dynamic model filtering and weight clipping, help to reduce the necessary level of noise that is necessary to remove the impact of backdoor. Without these first two steps, the defender will need a very large, will need to add a large Gaussian noise to the model, so to mitigate the impact of backdoor. And this will in turn result in a model with low accuracy because too much noise is added. Here we illustrate the properties of backdoor models in federative learning. So here we show the update of the global model, which is G with the white arrow here. And we denote three types of backdoor updates with the red arrows here. So W1 here is a backdoored local model that has a large angular deviation from the global model G to achieve the backdoor payload. The second property of backdoored local update is that here with G2, we show an example that the backdoor model has a very large magnitude compared to the global model. This large magnitude is a characteristic of backdoor because the malicious local clients needs to amplify its weight parameters so that after model aggregation, it has large enough impact to inject the backdoor. The third the third type of backdoor model is very stealthy, as we show by the arrow W3 here. It has a small angular deviation, and the magnitude of this local update is also reasonably small. So it does not fall into the previous two categories. Here we show the intuition of the flame defense. We have seen the properties of backdoor local updates in the previous slide, and flame designs three defense modules to mitigate or detect the impact of each backdoor. To identify the backdoor updates with large angular deviation, Flame has a dynamic model filtering module that computes the angular deviation of the local updates compared to the global model. So any local updates that has a large deviation with the global one will be marked malicious, and it is filtered out.
So Huili, I think we have only a couple of minutes left. Let's just try to wrap up because
okay.
we just want to go to the end and.
Okay. So I'll finish this part quickly, and then the second defense is clipping. So to mitigate the impact of large magnitude updates, Flame performs clipping, which downscales the weight updates of the second backdoor model here. As shown, W2 is shortened so that its impact is reduced. And to mitigate the third type of stealthy backdoor model, Flame use dynamic noising such that it adds proper amount of Gaussian noise to the model so that the impact of the backdoor update is diluted in the global model. Because of the time limit, I won't go through the details of another defense, which is called deep sight. The general idea is similar. It also has three defense layers, filtering out malicious models and clipping the weights of local updates. And then it performs cluster-wise aggregation to make sure that the malicious models are not aggregated into the global model. And it has 2 different modules that extract the characteristics of local updates. And these 2 properties are used as the features to identify malicious local updates. Okay. I will stop sharing now then.
Well, you can still share it, you know.
Okay.
Yeah. Okay. Is there any questions?
Hi.
Hi.
Good portion of your talk, you guys talked about like binary and discrete neural networks and the flip attacks. Are binary neural networks used in actual applications, or are they still a research area primarily?
I mean, as far as I know, they're being used in actual applications. In fact, you know, Apple bought for hundreds of millions of dollars one of the binary neural network companies. So I cannot imagine they just bought them for research value. I think they're using them for some embedded systems applications that are on device and need lower resolution. So the main thing with binary neural network is that they compromise the resolution, right? So you know, I don't know exactly off the top of my head where they're used, but from what I heard, the company that was bought by Apple, it was like I think 2 years ago, and now they're you know, they basically are the it's the part of Apple that is now in Seattle. They are, and this was funded from the University of Washington, Seattle. I believe that's being used inside Apple. In fact, I have one of my former students works in that group.
All right, thanks.
Mhm.
Useful information.